Okay, people, as I told you, during today's class, we wanted to check the information on hybridization. And so therefore, the goal for today's class is to understand hybridization. Okay, last class, using the chart from a living class, you were learning about this concept by memory. Today, we're going into the deep of this information. Let's go back to these things. The carbon atom, atom number 6 in the periodic table. Its electronic configuration 1s2, 2s2, 2p2. If we want to work only with the valence electrons, we're using the electrons in the last period. So this is 2s and 2p. What I'm going to produce here is our orbitals diagram. If you remember, you have 1 orbital for s, 3 orbitals for p. Using the way of arranging the electrons in the different orbitals, we should be placing 2 electrons in the s orbital, 1 electron in px, 1 electron in py. Hybridization. What does this word mean? It means making a mixture, making a hybrid. What type of a hybrid are we making here? We're making an orbitals hybrid. This is, let's mix the orbitals which originally have different levels of energy. How are we gonna be doing this? Really easy. We're gonna be moving this electron from here, from the s orbital to the p orbital. By having done this, we now have 4 hybrid orbitals. Having done this, we can now explain how the carbon atom is going to be really forming 4 different single bonds, all of them with the same energy. These 4 hybrid orbitals is what we're going to be referring to as the sp3 hybridization. Why the name sp3? Because you're using the s orbital and the 3 orbitals in p in order to form 4 single bonds. With this structure, this carbon atom would be forming what we've already learned would be being in the center of a tetrahedral structure. And this is the regular structure of the carbon when forming an alkane. That's it. sp3 hybridization. But we know that there are 2 other models of hybridization. There's a model that is referred to as sp2 and a model which is referred to as sp. How do these 2 models work? Also very easy. I'm sketching out once again that I had my 2s orbital, my 2p orbitals, and that I've already made a hybrid out of them 4. When the carbon atom is going to be bonding to another carbon atom by means of a double bond, or to an oxygen by means of a double bond, what we're going to be doing, as I had already explained, you're only going to be having 3 single or sigma bonds. This is a single bond, sigma. This is a single bond, sigma. This is a single bond, sigma. And we had said the double bond by itself is the pi bond, a pure orbital. What is this information meaning when seeing this sketch? It's meaning that you're using this s orbital and these 2p orbitals, s p2, to form the 3 single sigma bonds. Where do we have the pi or the pure orbital. This hybrid orbital, which you didn't use in making these single bonds, is what we refer to as the pi bond or the pure orbital, the pure electron. And that's this one that we're using here in order to form our double bond. The very same thing applies for the carbon joining the oxygen atom. This is a single bond, sigma, sigma, sigma. And this one, the double bond, is the one that you're going to be building by means of using the pure electron here, sp2. As easy as that. Last, we have the sp hybridization model. Why sp? You should be able to tell by yourselves. You have the 2s, the 2p, levels, sublevels on their orbitals. You have your 4 electrons. And how many hybrid orbitals are you going to be using in order to build the structure of an alkene with its triple bond? You're going to be using this hybrid orbital in S, this hybrid orbital in P. This and this are going to be my sigma or single bonds. And you have left 2 pure or pi electrons. With those 2 electrons, it is that you're forming your triple bond. And that's the idea of hybridization. Hybridization sp3, hybridization sp2, hybridization sp. Single bonds, double bonds, triple bonds. And the rest of the information that you already learned by heart by studying the information in the chart from living class. That's it.